So all the learning that we've been doing so far has been leading to this, chemical reactions. And that's what the core of chemistry is seeing how the things around us in the world react with each other. So a chemical reaction is any change in which one or more substances are destroyed or broken down and one or more new substances are made. Okay? So you have to start with something and then it must become something different. Okay? So you can very much relate this. Chemical reactions occur whenever a chemical change occurs because you are creating something new. Okay? So basic example of this, if you start with hydrogen and oxygen gas, then with the right amount of energy applied, you can make that become water. Okay? And that's a chemical reaction. So chemical reaction, it's very important that you get these straight. You start with reactants. Those are the substances that get destroyed or their bonds are broken. All right? And then those reactants, the atoms within them rearrange themselves to create new bonds to make products. Okay? So generally speaking, this is written in formula form where you have the formulas for your reactants with, so this is going to be the formulas for your reactants with an arrow pointing towards the formulas of your products. All right? If you are writing it out in words instead of symbols, you would say the arrow as yields. Okay? You can also say make, but just so that you're aware, because you will see yields more commonly, especially in textbook speak, things like that. Yields is the scientific word used for these reactants yield these products. A couple of really clear indicators that a chemical reaction occurs. Evolution of light, which means where there was light, there now is. Where there was not light, there now is. Okay? So if a chemical reaction causes light to occur, then we know, or if light comes out of nowhere, we know some sort of chemical reaction is going on. Okay? Example of this is, if you've ever been, a party or dance or something like that, and people have those little glow tubes. In order to get them going, they have to be cracked. And what that does is it mixes two chemicals together that produces the glowing. Another big thing is a temperature change. We saw this in our chemical change lab. When we mixed magnesium and hydrochloric acid, if you felt the bottom of the test tube, it got warm. All right? And it didn't get warm because we were heating it. It just got warm because those two chemicals got mixed together. That is a sign that we have a chemical reaction. Right? If it gets warm because you're heating it with fire, that's not a chemical reaction. Right? But if you have two substances that are at room temperature that combine and cause a temperature change by themselves, that's a chemical reaction. So, formation of gas. Right? Again, we saw that with the hydrochloric acid and the magnesium. All of a sudden, it gives off hydrogen gas, and you can see it because it's kind of cloudy and it comes out of the top. All right? Again, you know that that is a chemical reaction because we didn't apply any heat in order to evaporate something. All right? So one thing just to be clear, boiling is not a sign of a chemical reaction. That's a state change, that's a physical change. Okay? But when you have a formation of gases without heat, just two things at room temperature and suddenly there's a gas that forms, you know you have a chemical reaction. Color change. 99% of the time, if you're doing an experiment and a color change happens, it's because of a chemical reaction. Honestly, off the top of my head, I can't think of anything that wouldn't follow that rule of thumb. All right, the picture here is rust. We saw chemical changes a few times in that lab. There was the copper sulfate. When we broke the bonds of the water, they went from blue to white. There was the iron and the sulfur. When we heated that, it changed to red and then it changed to black. Okay, so color change is a good example of a happening. And then last one, this is a new word called precipitate. precipitate. And when a new solid forms, so generally speaking, what happens is you're going to combine two liquids, and all of a sudden you get a solid out. It's floating on the water or sinks to the bottom, but you can tell it's a solid. We saw this as well in that chemical change lab when we mixed the sodium chloride solution with the silver nitrate. Okay, so what ended up coming out was silver chloride. Okay, but this is a telltale sign when you mix two liquids together and get something else. Okay, and get a solid to come out. So just some kind of general descriptions. You can write out equations in words, all right, which is just, statements that indicate what your reactants and products are. All right, so in this case, instead of writing out symbols, we can say iron plus chlorine yields iron 3 chloride. All right, now I'll get into what the things in parentheses mean. So that's a word equation, or you can write skeleton equations, which would involve symbols or chemical formulas to identify the reactants and products. So instead of iron, we say Fe. Instead of chlorine, we say Cl. And then instead of iron 3 chloride, we say FeCl3. Okay? So all of this naming that we've been doing is so that you can write out these equations and understand what the equations mean. Okay? So what was in the parentheses is indication of the state. Because sometimes if you sit there and you take solid sodium chloride and mix it with solid magnesium, it's just going to sit there. No reaction is going to happen. Okay? But if you put the sodium chloride in a solution and mix it with magnesium, what will end up happening is you'll get magnesium chloride and give off, and then have sodium. Okay? So these state changes are important because they explain what state all of the chemicals need to be in for this reaction to work. Right? So most of them are pretty clear. S is solid, L is liquid, G is gas. Aqueous technically isn't a state, but it is sometimes a required way for the chemical to be presented to the other, meaning it's just dissolved in water. Okay? So like the example I gave with the sodium and the magnesium. In order to make magnesium chloride, you'd have to have aqueous sodium chloride. Okay? Dissolved in water. Do a little bit of practice. First one is write the formula for the reaction of carbon and sulfur to form liquid carbon disulfide. So, one thing to discuss in regards to state changes, if something's in its elemental form, I don't need to tell you the state, because you can figure it out off of the periodic table. Okay? We're always going to assume that this stuff is done at room temperature, because these are all reactions we could do in our classroom. So you just have to look at your periodic table. If it's in black, it's a solid. If it's in red, it's a gas. And if it's blue, it's a liquid at room temperature. So carbon is black on the periodic table, so that's going to be a solid, plus sulfur, which is also black on the periodic table, so that's going to be a solid, yields carbon disulfide. So we just covered our covalent bond naming. Since it's carbon without any prefix, how many should that be? Just one. And disulfide means 2 sulfides. And then we have to address the liquid, which should be like that. Okay? So I need to give you some indication on the state changes when it's a compound or, it's something that wouldn't necessarily be known by you. Okay? But some things you do know is carbon and sulfur and any elemental state, reactant or product. You can figure out what phase it's in by looking at the periodic table. Okay? So here's some practice with going from the formula and putting it into words. All right? So first off, let's fill in those blanks. So mercury and oxygen, they're both on the periodic table. So mercury is blue on the periodic table, which means that's going to be a liquid. And then oxygen is red on the periodic table, so that's going to be a gas. Right? Now, putting this into words, starting with, actually before we move on, I want to address this. Oxygen is written as O2 in its elemental form. If you remember, there was that list of diatomic elements. Alright, you're going to want to remember these. There's not very many. There's hydrogen will always be in a 2, nitrogen, oxygen, and then every single halogen. So fluoride, fluorine, chlorine, bromine, iodine, and astatine. Those all form diatomic elements. So they will never, if you put it into a formula, you should never put them in by themselves. You should always put them in these pairs, okay? When they are in their elemental form. When oxygen bonds with other things, like with the mercury, they can bond singly. It's just when it's by itself, it's always going to form a pair of 2 O's instead of just one, okay? So let's write this up. We have mercury oxide. If you remember, mercury is on that list of multiple possible ions. So we have to figure out our charge on our oxygen. O falls in group 6, which means it has 6 valence electrons. So it's going to take 2 more to get to 8. So this is going to be a 2 minus charge, which means mercury has to be 2 plus. So we're going to write mercury 2 oxide yields, so that's the word we use for the arrow, and actually I should put in front of here, solid mercury 2 oxide yields liquid mercury and oxygen gas. All right. So here are our reactants. Yields separates the reactants from the products. And here are products. Okay. One last thing, if you're having a hard time remembering which side is reactants and products, I always said this phrase to myself. You have to have something to react, called reactants, in order to produce something called products. Okay? Something has to react for you to produce something. All right? So make sure you do the online assignment, and I'll see you in class.